So another topic that's not going to be covered by our exams, but it's in the book. So let me mention a few things about it. It's on primitive roots. So let's see what a primitive root is. Primitive roots. So if I have a prime number, so let P be a prime number. A primitive root mod P is any integer, say B, such that powers of B generate all the non-zero residue classes modulo P. So for any number that's not 0 mod P, the number is congruent to a power of our B, such that for any M, any class M, any integer, let's say integer, M, with MP, GCD is 1, so M is not divisible by P. There exists positive integer K such that B to the K is congruent to M mod P. So let's see what this means for B to be a primitive root. And not numbers, not all the numbers are primitive root, are primitive roots. So for B to be a primitive root, it has to have this property that for any M, there is an exponent K such that B to the K is congruent to M. An example of a number that's not a primitive root is B is 1. See. Then I can take an M that I want, and then I try to find a K such that 1 to the K is congruent to M. No, 1 to the K will not be congruent to M. 1 to the K will be congruent to 1 all the time. So see, if I take M such that M is not congruent to 1, congruent to anything else, I cannot arrange for 1 to the K to be congruent. So 1 will not be a primitive root. Maybe no number is a primitive root because we are asking a lot. So now let's see. This is the definition. One definition, because there are several equivalent formulations. But let's see an example. There's a theorem saying that there are primitive roots, and a theorem that tells us how many primitive roots are there. But let's see first an example. Say P is 7. I look at powers of numbers modulo 7. Say 1 is not a primitive root. I check 2. Is 2 a primitive root? Is 2 a PR? Let's say PR means primitive root forms. Mod 7. Question mark. Well, I look at the powers of 2. 2 to the 0 is 1. 2 squared, 2 to the 1 is 2. 2 squared is 4, 2 cubed is 8, but 8 is congruent to 1. And then 2 to the next power is this times 2. It's going to be congruent to 2, congruent to 4. I'm only getting 1, 2, and 4. So 2 is not a primitive root. 2 is not a primitive root mod 7. Let's check 3. Is 3 a primitive root mod 7? 1, 3, and I multiply by 3 all the time. 3 squared is 9. That's congruent to 2. Then maybe I should write it like this. For each k, I let k to be 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. And for each k, and 0, of course. 0. Let's k is any of these numbers. And here I compute 3 to the k. And of course, I still word mod 7. Mod 7. 3 to the 0 is 1. 3 to the 1 is 3. Fermat's little theorem tells us that 3 to the 6 is congruent to 1 mod 7. So that's the connection with what we did before. So 3 to the 6 is congruent to 1. So once I know that 3 to the 6 is congruent to 1, 3 to the 7 is just you multiply by one more factor of 3. It's going to be congruent to 3. 3 squared is congruent to 9, or is 9, it's congruent to 2 mod 7. So 3 to the 3 squared is congruent to 2 mod 7. And if I multiply this by 3 to the 6, I get, if I get 3 to the 6 is congruent to 1 mod 7. This is Fermat's little theorem. This is what we computed in this case. If I multiply these two congruencies, I'm getting the 3 to the 8 is congruent to 2 times 1, which is what we saw earlier. That is to say, after 6, after 3 to the 6, so after 6, after the exponent is 6, larger power, they start to become periodic automatically by Fermat's little theorem. It could become periodic earlier, which is what happened in the case of 2. So 2 to the 0, 1, 2, 3, 4, 5, 6, 2 to the 6 was still 1 by Fermat's little theorem. But I get a 1 earlier. So the sequence became periodic with a smaller period. And what happens in general, for each number, modulo each number relatively prime with p, has a certain period, modulo p. You multiply by the number or raise the number for various powers until one of these powers is 1. And once the first power, it's 1, this is congruent to 1, that will be the order of our number. And after that, it becomes periodic. So 2 to the 0, 2 to the 1, 2 to the 3. 3 is the order of our number 2. It's too small. For a primitive root, I need something that's not small, so it has a chance to cover all the residue classes. So that's another interpretation of primitive root. It's something that you cannot raise that number to any power less than p minus 1 to be congruent to 1. I'll write that in a moment. But let's complete this computation. 3 cubed is 27, mod 7, 21, 27, 6. Oh, I should have just multiplied this by 3. 6 times 3 is 18, mod 7, 44. And 4 times 3 is 12, mod 7 is 5. Yes, and we have our primitive root. So 3 is a primitive root mod 7. Any number I choose that's not a multiple of 7 is congruent to a power of 3. If I choose my m before to be 5, yes, I find the power. 3 to the 5 is congruent to 5. If I choose my m to be 6, yes, I have 3 to the 3. 3 cubed is congruent to 6. So now we see that there are two equivalent formulations. One is that the powers of 3 generate all of them, and the other formulation is that this sequence is periodic with period 6, but not with a smaller period. And this formulation can still be reformulated as saying that the first time when 1 appears is exactly when you take 3 to the 6. So let's rephrase this. Maybe I keep this example because I want to see if there are any other primitive roots. So then we have this fact or theorem or whatever, or a new definition if we want. B is a primitive root mod P if and only if the smallest integer, in the sense that the smallest exponent, k, for which b to the k is congruent to 1 mod p, is k equals p minus 1. Of course, k equals p minus 1 is one such exponent by Fermat's Little theorem. B to the p minus 1 is congruent to 1. The question was, is b to something smaller than p minus 1 still congruent to 1? If that happens, then b is not a primitive root. If that doesn't happen, 3 to any smaller power, of course 3 to the 0 is 1, 3 to the p minus 1, that's 6, is 1, and in between nothing, 3 to anything else, it's not 1. Then 3 is a primitive root. That's very simple. Now, there may be other primitive roots. And not only there may be, there are other primitive roots. And their number, the number of primitive roots, well, of course, there are infinitely many primitive roots because I can, if b is a primitive root, I can add any multiple of p to b and it still satisfies the same congruence. So once we know that 3 is a primitive root, then of course 3 plus 7 is 10, it's a primitive root, plus 7 is 17, plus 7 is 24. All these are primitive roots, mod 7. But in practice I need 1. And once I have 1, and to find 1, of course, it's enough to focus on this interval from 1 to p to find 1 primitive. There's a nice general theorem telling us how many primitive roots are, and exactly the Euler function, not of p, but of p minus 1. So there are let's say a theorem. There are exactly, I said Euler function computed at p minus 1, primitive roots mod p, this is p minus 1, that are not congruent to each other. Because otherwise there are infinitely incongruent primitive roots. So in the interval from 1 to p, there are exactly p minus 1. In our case, as an example, when p is 7, Euler function, if you have p minus 1, if you have 6, and this is 2. I can compute it by using our general formula for computing the Euler function, or I can just use definition. It's the number of numbers, positive integers up to 6 that are relatively prime to 6. So I have 1, 2, 3, 4, 5, and 6. Those that are relatively prime to 6 are just 1 and 5. So there are 2 primitive roots. We discover that 3 is one of them. Now, and 2 is not one of them. Which one is the second primitive root? Now, there's another nice part of the theorem telling us that once we find the primitive root, we can find all the other primitive roots by raising this primitive root to exactly those powers that are relatively prime with p minus 1. So in our case, our primitive root that we found is 3. So I come back here and I say 3 to the 1 is 3. So 3 is a primitive root, but I can get the other one, is 3 to the 5. Is the other primitive root. Is the other primitive root. The other PR, primitive root. 3 to the 5 is the other primitive root, but that's congruent to 1, because I want the primitive root in a small primitive root in the interval from 1 to 6. 3 to the 5, 3 to the 5 is 5. You see, 3 to the 5 is congruent to 5. That's congruent to 5. Mod 7. So 5 is the other primitive root, and I want to check now, I want to erase everything just to check that 5 was indeed the other primitive root. So I look at powers of 5. So k is 0 or 1, 2, 3, 4, 5, 6. There's no need to put a 6, but okay. 5 to the k. Because by Fermat's little theorem, we already know that 5 to the 6 is congruent to 1. We still work mod 7. So our prime is 7. So 5 to the 6 is congruent to 1. 5 to the 0 is congruent to 1. And all I need to check is that 5 to nothing else in here is congruent to 1. And then we also show that the other definition of the primitive root holds. That powers of 5 will provide us with all the residues, all the non-zero residues mod 6. Let's see, let's multiply by 5. 5 times 1 is 5. 5 times 5 is 25. But modulo 7, 21. 25 is 21 plus 4. 4. 4 times 5 is 20. 20 mod 7, 14 is the multiple of 7. 20 minus 14, it's 6. It's congruent to 6. 6 times 5 is 30. That's 28. A multiple of 7. 20 plus 2, the 2. And 2 times 5 is 10. Mod 7. So 10 minus 7 is 3. And indeed, no 1 appears here in between these two. And all the numbers, all the residue classes appear. So this is how we can find all the other primitive roots if we have 1. Now let's see one possible application of primitive roots. There are other applications, but one application is this. Unfortunately, I removed exactly what I needed. So the reason, one of the main reasons why logarithms were invented was to make life easier for people who need to do computations. It's easier to add than to multiply numbers. So, for instance, if I have to multiply 2 numbers, like, I don't know, the basic property of the logarithms is that logarithm in any base, say, like natural logarithm, ln, of a product of two numbers is ln of A plus ln of B. So suppose we have, nowadays, when we have all these powerful computer programs, multiplication is not that difficult to perform. Still, addition is faster. Several hundreds, quite a number of hundreds of years ago, when logarithms were invented, it makes a lot of difference if you have to add two numbers that are very large or to multiply. So if you have two numbers like 1, 2, 7, 3, 4, and then on period 2, 1, 9, 6, I just made some numbers. And then you have to multiply this by 3, 5, 1, 9, 2, 5.712 or 1, 2, 3, and so on. Say it's this two numbers that need to be multiplied, and I need to find this number. If we have already a table, of logarithms, and there were people at those times who computed large tables of logarithms, then you would do like this. You say, oh, suppose this is my number A, this is my number B. I look at the table will tell me what natural log of A is, 223.41, it's not, you just make up some numbers. The logarithm of B, ln of B, is say 3.512 and so on. So you don't compute anything so far. You look at the table, see what the logarithm of this is. Look at the table, see what the logarithm of this is. You add up those two logarithms, and we get natural log of A plus natural log of B is equal to whatever the sum is. So you add two numbers instead of multiplying two numbers. And it's 27 point whatever. Then you look at the table again and see where this number appears in the table. The tables were listed in increasing order. You know how many, a few digits, how many digits they had at the time. You look at the table and it gives you a number. The number whose logarithm is this number. But the number whose logarithm is this number, we know that natural log of A plus natural log of B is in fact natural log of AB. So the number that you find in the table will be exactly AB, because that number has the logarithm of this. We can apply this if we work modulo prime. Now, a prime is as small as 7. I'm just going to do this mod 7 just to check this. If I have a primitive root, because if I have a primitive root, I can write each number as a power, as an exponent, and that exponent behaves like a logarithm. Of course, it's not useful. It's too much work in this case, but if one works with prime numbers that are larger, like 100, like a prime number that has 100 digits, that's bigger than 10 to the 100, that's a huge number. And it makes sense to try and replace multiplication by addition. So, but if you do have one, primitive root modulo that prime, then you can do this. So let's again take P to be, let's say P is 11. What is a primitive root mod 11? Is it 2? I'm just checking. Mod 11. 2 was not a primitive root mod 5. Let me see. Powers of 2. 1, 2, 2 square. That's 4. 8. 16 minus 11 is 5. Times 2 is 10. Times, yes, it does look like a primitive root. Okay, let me make the table. This is a primitive root. Because what happens is the order of the element. The order of the element divides the order of the group in general. That's a group, it's a multiplicative group with 10 elements, the so-called residue classes modulo 11 that are not zero. They form a multiplicative group. And for a number to be a primitive root, it's the same thing as saying that it's a generator of that group. That group is cyclic and is generated by one element. That's what it is from a, say, more conceptual point of view of say, group theory. It's a primitive root. It's any generator of the group. So if 2 was not a primitive root mod 11, then 2 to the 10 is not the smallest power of 2. So the order of 2 is not 10. It's enough to multiply 2 by itself a smaller number of times. But because the order of the group, the order of 2 divides the order of the group, the first time when 2 to some power it's 1, or anything to any power it's 1, it has to be a divisor of this p minus 1. So a divisor of 10. But I just computed the first 5. None of them was 1, and there are no other divisors. So now I do this properly. I just explain why I knew already that 2 is a primitive root just by checking 2 squared, 2 to the 5. Let's compute now all, and let's use this to see this application of the theory involving so-called logarithms. This is a logarithm modulo primes. So now I take powers of 2. 2 to the 0. So k is 0, 2 to the k. Mod 11. K 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. 2 to the 10 is 1. I must leave the theorem. And I'm saying that if 2 to something is 1, 2 to the 0 is 1. 2 to the 1 it's not, it's 2. If 2 to something else is 1, that's something else. The first time when 2 to something is 1, that something has to be a divisor of 10. So either 2 to the 5 or 2 squared. 2 squared is 4, a congruent to 4. And I computed up to 2 to the 5. 2 to the 5 is actually 32. Mod 11, 32 minus 22 is 10. It's not 1. So then I knew, oops, this is actually a primitive root. That's good for us. Let's find all these powers. Powers of 2. 2 cubed, 8 times 2 is 16 minus 16 minus 11 is 5. Times 2 is 10, times 2 is 20, minus 11 is 9. Hope I'm not making any mistake. You better check, double check. 20, it's congruent to 9. 9 times 2 is 18, 7. Minus 11 is 7. Times 2 is 14, minus 11 is 3. Times 2 is 6. And I should have all the numbers from 1 to 10 in another order. So 2 is a primitive root. 2 is a primitive root, mod 11. It generates all the non-zero residue classes, mod 11. But now let's see, can I use this primitive root? Suppose I make one table, I find one primitive root, a prime is given. Then I want to be able to do all sorts of multiplications without doing any additional computations here. So in the same way, I want to replace a multiplication by an addition. So suppose I do the following thing. I multiply this. 8 times 9. These two numbers. And I want to see what this is modulo 11. So 8 times 9 is 72. What's 72 mod 11? 6. Because it's 72, it's 66 plus 6. So it's congruent to 6 mod 11. But we need to multiply them. I want to replace this by addition, they will give us exactly the same number 6. Okay. So, to do this, I look at my table. 2 to something will be congruent to 8. 2 to, I look for the table, 8 is here. 2 cubed is congruent to 8. Now, 9. Where is 9? 2 was a primitive root, so it generates everything here, including 9, if I need 9. 2 to the 6. See, 2 to the 6 is congruent to 9. So I found these two numbers, 3 and 6, like that. Like 2 to the 3 is congruent to 8. It's not 8. But 3 is like a logarithm in base 2 of 8. Base a primitive root, modulo. That's the thing. Anyway, I look at the table, I didn't compute anything, and I saw that 8 is 2 cubed, and I saw that 9 is, where's 9? 2 to the 6. So now I write this as 2 to the, and now I add the two exponents. So you see, instead of multiplying two numbers, I add two numbers. And it's 9. 2 to the 9. Oh, then I look at the table. 2 to the 9. Where is this? It's 2 to the 9 is 6. So it's congruent to 6. 1, 11. So I look at the table several times, and I got it. And I did one addition instead of a multiplication. Before I end this video, please have a look at the length. We don't want the length to be...
It's half an hour.
Oh, okay. I can take a few minutes
Yes.
to relax, if you don't mind.
Sure.
Tell you a story.
Okay.
I don't know if I mentioned this in class, probably not. But better close the door. Nothing confidential about this, but this it's a story from a long time ago. Because I remember why multiplication and addition are like that. When I graduated from the University of Bucharest, I immediately got a job. Actually, that was the law. You first of all, you are a math major, you graduate, then you get to work as a school teacher for a couple of years, for 3 years, that was the law, even if you get another job. And you cannot work as a school teacher wherever you want. Those times it was like this. If 103 people graduate, there will be exactly 103 jobs available in the entire country of Romania. So you choose one of those. Anyway, I chose one. I report to work a few days before classes start. And the principal of the school, it was a high school there. I was supposed to teach mathematics, all these classes they have. And the teacher says, the principal says, you have to give a grade for one of our students who never comes to school. I said, you give him a grade for last year. He never came to school, but I need a grade now, before the beginning of the new academic year. So I said, but if he never comes to school, how do I give him a grade? He said, well, you go, get him from his home, bring him here, give him an exam and give him a grade. And he wrote the name on a piece of paper. It's a true story, I'm not making this up. And his address, and he said, okay, this is the place, I give you a map, you go there. So I said, yeah, but this is the job for his last year teacher, he should go there. He said, yeah, but he's afraid. So I said, oh, wait a minute, he's afraid? Yeah, but now he's in your class, so it's your responsibility to go. So I said, okay, but in that case, let's all go. All his teachers, we all go, we bring him to school, we give him exams. I give him a math exam, I give him a grade. And he said, no, everybody is afraid to go there. It's a very dangerous neighborhood. You have to go alone. So I said, I remember exactly what I said. Okay, I go, but you give me police protection. Give me call police, ask police to come with me, we bring him to school, I give him an exam. You know what he said? Police is afraid to go there. It's a dangerous neighborhood. So I said, the police is afraid to go there? You want me to go there? He said, yes, the law doesn't say police has to go there. The law said you have to go there. So, what law? Well, he's in your class, so you have to give him a grade. In order to give him a grade, you have to give him an exam. In order to give him an exam, he has to be in school. And in order for him to be in school, you have to go bring him to school. It didn't sound right, but anyway, I panicked and I said, okay, yeah, okay, I'll do this. Give me a map. So I went there. By the time I got there, that neighborhood, it was completely dark. I don't know what I'm doing. I go on those streets, there is no light, so it's complete darkness. And at some point I kind of see several people running towards me from various directions. Maybe 8, maybe 10, I do not remember now because it's so many years ago, but I remember I counted there were at least 8. So there was no way to run. They came from all directions quickly and they surrounded me. And I said, I didn't say anything. One of them pointing a knife at me and said, what are you doing here? So I said, well, I showed him the piece of paper. I said, I'm looking for this person. That's his address. Can you show me? He said, we take you to our boss. So I said, well, that's very nice of you, but I don't need to see your boss. I need to talk to that person. The student who never comes to school. I said, need to talk to... No, you don't need to talk to him. You come with us. And I realized what grave mistake I made. I didn't know what to do. I said, well, maybe it's not that important to talk to him today. I think I go now and I come back some other time. He said, no. It's too late for that. You come with us. Several pointing knives at me, and I said, okay. They took me to a place that was like a very old house, and inside there were many other people looking just as frightening as these guys, and this guy goes and tells someone there, hey, boss, this guy is looking for your brother. So the student who never comes to school was the younger brother of the leader of this group that was terrorizing the neighborhood. So the boss asked me, who are you? And I say, I'm his math teacher. And then he said, not laughing. I'm laughing now, but it was traumatizing experience. He said, look, we don't like teachers. Oops. And when he said we don't like teachers, I felt this 8, 9, 10 guys coming closer to me, kind of invading my private space. And then he said, and he continued, he said, we don't like math. And this guy coming closer, literally breathing down my neck. And he said, so you are the worst kind of teacher. I didn't say anything. So what do you want? He said. In my mind, I was like, the only thing I really want, if possible, is to get out of here alive. But I didn't say this. I said, well, I came to take him to school, give him an exam. And he said, what? Are you crazy? And I said, he doesn't have to come to school. I can give him an exam right now. And he said, what? And I said, well, just a small exam. He again said, what? And I said, just very small exam, just multiply 2 numbers. And again he said, what? And I didn't know what to say after that. And then I said, well, then maybe add 2 numbers. Because it's easier to add numbers. That's why I was reminded of this. And he said, what numbers? And I got an idea. I said, well, you're the boss, you choose the numbers. So he said, I remember the numbers 5, 7. He said, 5 and 7 are good enough for you? And I said, oh, yes. I have this piece of paper, which the principal gave me. Can you write on the paper? Let's write 5 plus, write directly on my hand. I put the paper on my hand. I have this. I have a pencil here. Can you write 5 plus? But he couldn't write. My hand was shaking. You can imagine. I was like this. But he was he write 5 plus 7, and I said, okay, let's write equal. This is 9th grade. But I wasn't sure if he was able to do this. I didn't want any more trouble. And I told him, let's write equals 12. 12. He wrote 12. And I said, okay, that's good enough. Perfect. Now I can leave. As a side comment, our exams will be a bit harder. That's nature of this business. Okay. But while I was leaving, the boss yelled at me. He said, stop right there. And then I really panicked. And I turned. I was just ready to leave the room. And I turned and he said, he didn't sign the paper. Oh, so I turned and I left and I said, he doesn't have to sign. You're the boss. You saw, you're eyewitness. So it's perfectly legal. And that was it. I never returned. Oh, maybe we should start with this story.